anytime you're trying to come up with a mechanism for a reaction, it's worthwhile to study a little bit of what you are starting with and then thinking about what you finish with and think about what is different. So what we're starting with, we could call this 1, 2, 3, 4, 5. So this is, let's see, we have a methyl group on the number 2 carbon. It is a pentene, and that's double bond between the number 2 and number 3 carbons. So this is 2-methyl, 2-methyl, pent-2-ene, pent-2-ene. So that's what we start with. We're in an acidic environment. It's going to be catalyzed by our hydronium here. And we end up with this. And how is our product different from what we started with? Well, the double bond is now gone. The number 3 carbon gains this hydrogen. And now the number 2 carbon gains a hydroxyl group. So one way to think about this is in the presence of an acid, it's acid-catalyzed, we have gained 2 hydrogens and an oxygen, which is, well, we've gained what could be used to make a water. And this is actually called an acid-catalyzed addition of water. The water isn't sitting on one part of the molecule, but if you take the hydrogen we added and the hydroxyl we added, if you combine them, that's what you need to make a water. So let's think about how this actually happens in the presence of our hydronium. So let me redraw this molecule right over here. So let me copy and paste it. And that's not exactly it yet. That is just with the single bond. So let me draw, whoops, wrong tool. Let me draw the double bond there. And now let me put it in the presence of some hydronium. All right, so we have an oxygen bonded to, so this would just be water. Oxygen has 2 lone pairs. But hydronium is a situation where the oxygen is sharing one of those lone pairs with a hydrogen proton, thus making the entire molecule positive. Because the hydrogen, you could view if the hydrogen proton was positive. So there you go. This now has a positive charge. And this can be pretty reactive because we know that oxygen is quite electronegative. It likes to keep its electrons. So what if there was a way there's a way for the oxygen to take back the electrons in this bond right over here, the 2 electrons in this bond? Well, what if one of these carbons, especially the ones that have the double bonds, what if some of the electrons from this double bond could be used to take that hydrogen proton, and then oxygen can hog its electrons again? And you might say, well, that's reasonable, but which of these carbons would actually do it? And to think about which of those carbons would do it, we have to turn to Markov-Nikov's rule. Markov-Nikov's rule tells us that, look, if you have a reaction like this, an alkene reaction, the carbon that's already attached to more hydrogens is more likely to gain more hydrogens. The carbon that's attached to more functional groups is more likely to gain more functional groups. Another way to think about it is think about, well, what is the order of the carbons? Because the higher order of the carbon, the more stable it will be if it forms some type of cation. So if you look at this carbon right over here, our number 2 carbon, let me circle it. Our number 2 carbon is bonded to 1, 2, 3 carbons. So this is a tertiary carbon. This one right over here, this carbon on the other side of the double bond is only bonded to 1, 2 carbons. So this is a secondary carbon. So the tertiary carbon is going to be more stable as a carbocation. You can think of it as it can spread the charge a little bit. So it would be more likely to lose the electrons in one of these bonds. And so the way that we could think about this mechanism, and it might be a little bit clearer when we form the carbocation, is I'll do this in blue. Let's have these 2 electrons that form this bond. Well, now they form a bond with that hydrogen. And now the oxygen can take back these 2 electrons. And what is going to result? And I'm drawing an equilibrium. Remember, all of these things are going back and forth depending on how things bump into each other. But what are we left with? So let me copy and paste this again. And I'm copying and pasting it in a way that you can view this as the backbone, and I'll add what I need to add. So once this happens, we have this carbon, the number 3 carbon, now, whoops, I keep using the wrong tool. The number 3 carbon now forms a bond with this hydrogen, just like that. This carbon, our number 2 carbon, has lost an electron. It's no longer sharing this bond. And so now it is going to have a positive charge. It is a carbocation, and once again, it is a tertiary carbocation. It is bounded to 1, 2, 3 carbons. That is stable, more stable than if we did it the other way around. If this one grabbed the hydrogen somehow, then this would be a secondary carbocation. It'd be harder for it to spread that positive charge around. And what about our molecule up here? Well, let's see what it looks like now. We have our oxygen bonded to the 2 hydrogens. It had one of those lone pairs, and now the electrons in this bond are now going to form another lone pair. So it took back an electron. Or you could think of it, it gave away a hydrogen proton. And so this is now just neutral water. And we see that we have a conservation of charge here. This was positively charged. Now our original molecule is positively charged. And what feels good about this is we're getting close to our end product. At least on our number 3 carbon, we now have this hydrogen. Now we need to think about, well, how do we get a hydroxyl group added right over here? Well, we have all this water. We have all this water floating around. I could use this water molecule, but the odds of it being the exact same water molecule, we don't know. But there's all sorts of water molecules. We're in an aqueous solution. So let me draw another water molecule here. So the water molecules are all equivalent, but let me draw another water molecule here. And you can imagine it's just if they just bump into each other in just the right way. Water is a polar molecule. It has a partially negative end near the oxygen because the oxygen likes to hog the electrons. And then you have a partial positive end near the hydrogens because they get their electrons hogged. So you can imagine the oxygen end might be attracted to this tertiary carbocation. And so just bumping in just the right way, it might form a bond. So let's say these 2 electrons right over here, let's say they form a bond with that number 2 carbon, and then what is going to result? So let me draw. So what is going to result? Let me scroll down a little bit, and let me copy and paste. Whoops. Let me copy and paste our original molecule again. So there we go. So what could happen? So let me construct it actually. So we have the hydrogen there. We have the hydrogen. Now this character, so we have the water molecule. So oxygen bonded to 2 hydrogens. You have this one lone pair that isn't reacting, but then you have the lone pair that does do the reacting. And so it now forms a bond. Oops, let me do it in that orange color. It now forms an actual bond. And we're really close to our final product. We have our hydrogen on the number 3 carbon. We have more than we want on our number 2 carbon. We just want a hydroxyl group. Now we have a whole water bonded to the number 2 carbon. So somehow we have to get one of these other hydrogens swiped off of it. Well, and that could happen with just another water molecule. So let's draw that. So another water molecule someplace. I'll do it in a different color just to differentiate. Although, as we know, water, well, it's hard to say even what color is water if you're looking at the molecular scale. So here we go, and we're really in the home stretch at this point. You have another water molecule, let's say, let me pick a color. So let's say these electrons right over here, maybe they form a bond with that hydrogen proton, and then the electrons in that bond can go back to form a lone pair on that oxygen. And then what are we left with? And this really is the home stretch. So we are in equilibrium with, so let me draw my 5 carbon. So let's see, I have H3C, carbon, CH2, CH3. I have a CH3. I say H3C instead of CH3. I wrote it that way just so it's clear that the carbons are bonded to the carbons. You have You have the original hydrogen right over there. You have the one that we just added as part of this mechanism. You have this orange bond to now this hydroxyl group, the hydroxyl group, and it had one lone pair before. It had one lone pair before, but now it took both of the electrons from this bond to form another lone pair. Which I am depicting in pink. And then this water is now, or this water molecule is now a hydronium molecule. So let's draw that. So this is now oxygen, hydrogen, hydrogen. Had one lone pair that didn't react, but it had one lone pair that I put in blue that is reacting with this hydrogen proton, with that hydrogen, just like this. And so since it got the hydrogen proton, it's giving its sharing its electrons now. Now this has a positive charge, just like that. Oh, I have to be very careful. In the last step, I forgot to draw the positive charge. You always want to make sure that your charge is being conserved. We started off with a positive charge on the hydronium. Then we have the positive charge on a tertiary carbocation right over here on a number 2 carbon. And now we have the positive charge would be right over here, because that oxygen, what we saw before, that oxygen, which this water molecule was neutral, but you could view it as, well, now it's going to be it's now sharing these 2 electrons instead of keeping them. So you could view it as maybe it's giving it away an electron. And so now it becomes positive. And then the positive charge finally gets transferred to that other water molecule when it becomes hydronium. But just like that, we are done. We have added a hydroxyl group and a hydrogen combined. That's a water, so that's why we call it water, addition of water, and it was catalyzed by acid. So it's acid-catalyzed addition of water.